any question regarding this backing? Is it okay? Can you understand well? Yeah, if you have any question, just let me know. Yeah, okay. Okay, then we can take a look at if we use back into that the hard data, what is it look like? So this is the showed the results. The x-axis denote the number of the traits. Certainly, and this is the classification errors. Yeah, we can take a look at it. You can see. This is if we use this dashed. This dashed line just denote the test errors for the single tree. Then we can take a look at if we use the bagging, you got this one, this black one. Yeah. Certainly is better than the single tree, single decision tree. Then we can also take a look at another method. It's called the random forest. Very quickly we will introduce it. It performs better. This will outperform the back and the single decision tree. Then we can also take a look at the result. It's called this OOB out of the bag. Yeah. So you can say when you do the bootstrap, certainly some of observations have been selected as a part of the bootstrap samples. Someone not caught, have not been selected, then we call it out of bag. So you can take a look at it. If we use the just like the cross validation. This is the remaining observations not used to do this kind of model fitting. Then you can find this is the error rate based on this out of bag observations. You can see the bag is this blue one. You can say they have the very lower rate. For the random forest, the green one, yeah, you have much lower than this error rate for the decision tree. And this is a little bit of details. So here is a result for the back and the random forest for this hard data, the test errors. This is the black and orange are showed as the function of the B. Certainly that is the how many traits you have built, the capital B there. Okay. And number of bootstrapped the training set is used there. For the random forest, certain later we will explain. They do not. They worked with the predict the number of the predict, not the whole predict. They use just the m, the number of the m predict. So that it's just the square root of the p. And the dashed line indicate this kind of the error rate. This is resulting from the single decision tree. Yeah, single decision tree there. And the green and the blue, this is the blue, the single and the blue, this is the traces. They just shows the out of bag OOB error, which is this one. Certain later we will explain a little bit more. This is okay. Okay. And then we can explain a little bit out of bag error estimation. Certainly for this bagged model, this is very straightforward to estimate this test errors. You know, for the bagging, the K is the tray are repeatedly fed to the bootstrapped subset of the observation. Yeah, so one can show on average each bagged tray will make use of around the 2/3 of the observations. Yeah, this is you guys for the homework you have done this kind of calculation. So for the bootstrapped set, you can only use around the 2/3 of the observations. The remaining 1/3 observations not used to fit this is the given bagged tree. Actually, I referred we call it out of the bag observation. just like you do this kind of the k-fold cross validation. Here, just like the threefold cross validation. Two-thirds observations used to build the tree, and the remaining one-third observation you do this kind of to estimate the errors. Yeah. So we can predict the response for the ith observation using each of the tree in which the observations are all the out of bag. The error estimate based on this kind of out of bag observation certainly essentially is just the k-fold cross validation error for the bag. If this B, the capital B, the build tree is not enough, or the number of the bootstrapped observations is the bootstrap samples is large. Okay, this is about this the bagging. And actually, then we can introduce the random forest. This is also a pretty popular method. Random forest method actually provides an improvement over the bagged trees. By which this is just a small trick that decooperated the trees. So that we will reduce the variance when we average the trees. You can say, as in back, we will build a number of digestion trees on the bootstrapped training samples. But when we build this digestion trees, each time a split in a tree is considered. And so certainly here, the predictor we will randomly select m predictors is chosen as your split candidate from the full set of the p predictors. This split is allowed to use only one of the m predictors. Only one of this m predictors there. So you can say this say there. You just do a little bit of comparison what happens. So you can say you can say for this digestion tree, if we given this kind of bootstrap, given a bootstrap sample, then how do we build this kind of digestion tree? Build this digestion tree. Certainly for this kind of for this internal load, we did choose what? We did choose the xi, your predictor, and your cutoff point. That's true. The only thing for this xi, how do we choose it? Usually we select it from a set of the all predictors, like say x1, x2 up to the xp. You can say before each this kind of the internal load, when we do the predictor, when we do this kind of the splitting, we just choose this predictor from the full set of the predictors. So finally, definitely it's just make sure. Finally, this kind of the algorithm you learned. Like say this pi had star. They are correlated. They are correlated to each other. Sometimes they have a little bit higher correlation. Because you can say they use using the same selection process there. But here for this random forest, how do they do? For this random forest, certainly they say, okay, I will not select from this kind of the m predictor. So we say, okay, let's do a random selection of m predictor. From the full set of the p predictors. From the p predictor. So you got to say, okay, I got to like say, I just choose it like say, this is x1 star, x2 star, up to the xm star. You got this m predictors. Then when you do the splitting, you will choose your, when we do the split, then you will choose your this predictor xi, you just from this set. This is random select set, choose your predictor. So then you can easily say, then certainly you just compare this kind of two, this kind of splitting. Their overlapping will be pretty low. You quickly say might be for this set. This is the predictor, like I say, x1. Okay. Like I say, this is the x1. Let's simply say x1, x2 up to the x10. We just choose the 10 predictors. Then certainly you say next, this is the first one. Next one you might be just choose, like I say, x1, x5, then x9, about the x20, or like I say, like the 1000. This is, like I say, this is, you can say, if this way they only have for this two, this kind of the candidate predictor set, they only have the three predictors. They are the same. So you can say for this two, this kind of the candidate, for this two candidate sets, their overlapping is pretty low for this predictors. So if you do this way, definitely you can decorporate this kind of decorporate the correlations between the two, this kind of the fitted model. So this is this idea. Yeah. Okay. So this is this idea. So okay. So because we only choose a very small numbers there. So this m, this roughly empirically is just shows the square root of p. This kind of number will be considered in the each split. You can easily imagine if p is like say 10,000, then certainly this m only the 100. So you just say, okay, I just randomly select the 100 predictors from 10,000, from the total 10,000 predictors. So that's certainly you just compare this kind of two, this kind of the random selection. Their overlapping will be pretty low. Yeah, their overlapping will be pretty low. Yeah. So this is a reason. Yeah, by using this trick, we can decorporate this kind of the decorrelated this kind of the fitted algorithms. Yeah. This is okay. Yeah. Okay. And then we can take a look at this result. Yeah, this is the example. Is a gene expression data. We will apply this kind of random forest to the high-dimensional this biological data set. This is consisting of the expression measurement of this around 5,000 genes measured on the tissue samples from this kind of 349 patients. Below in the humans, there are around like 20,000 genes, and the individual genes have a different level of the activity or expression, in particular like the cells, tissues, or the biological conditions. Each of the patient samples has the qualitative label with the 15 different levels, either the normal or one of the 14 different type of the cancers. This one there. We use the random forest to predict the cancer type based on like 500 genes. This 500 genes has the largest variance in the training data. This yeah, this we just say, okay, if it has the largest variance, then usually these genes can explain the data well, can play the main role there. You can easily say, if some gene has this kind of variance is 0 in this training data, this just means this is for this gene expression almost constant. If it's constant, definitely it will have a low role there. Okay. We randomly decided the observations into a training and a test set and apply this random forest to the training set for the three different values of the this is three different values of number of the splitting variables. This M. Yeah, we can say here. We consider these three values. One is M is equal to the P, so that is around the 5,000 gene. Another one we use a half P, so that's around the 2,500. Then third one is the M square root of M, square root of P, so that's only around like the 70 genes. So you can take a look at their. This still is the test clarification rate. You can say if we use the M is the square root of P, you can say this is the green one. This is the best one. Yeah. You can also take a look at this blue and this orange. So they're almost the same. Even though you for the M is the half of P. Yeah. Then they're almost the same. Yeah. But if you use this one, square root of P, you improve this performance a lot. Yeah. Okay. This is a little bit of details of this graph. This is result we got. Okay, sorry. Yeah, this is we just have to do the selection. This is P only the 500. So P over 2 is 250. So square root of P is around like the 22, 23, like this kind of around the 20s. This is sensitive. Yeah. The test error is displayed as a function of the number of the traces. So each colored line corresponding to the different value of the M, the number of the predictors available for splitting at each internal real load. Random forest certainly did this kind of slight improvement for backing if you use the whole thing that's a backing. So this orange curve corresponds to the backing. Yeah. Okay. Certainly a single classification tree here have this error rate is around the 46%. So you can say this here, it become much better. You can say it's back you compared with low matter compared with a random forest or back, it become much better. Yeah. Okay. Any question? No. Okay. Okay. Then we can. This is for the random forest. So certainly it's just a little bit this kind of the small trick. Yeah, but you can improve it a lot. Yeah, this is a small trick there. So here when we do the splitting, we do not consider all possible predictors. We only consider small number of possible predictors. Then from this way decorrelates this tree. So finally we can use this idea to calculate the average of the observations. You can improve your variance a lot. Yeah. This is for the random forest. Yeah. And then we can take a look at the last method about the boosting. Yeah. This is for the boosting, just like the backing. This is a general approach, can be applied to the many statistical learning method for the regression or for the classification. Here we only discuss the boosting for this regression. Yeah. For this kind of the decision tree, for the regression decision tree, we know the backing involves creating the multiple copies of the original training data set using the bootstrap, fitting a separate decision tree to the each bootstrap sample, then combine all these traits together to create the single predictive model. Yeah. So certainly here each tree is built on the bootstrap data set. independent of the other traits. But boosting not like this way. Boosting works in a certainly in this detection tree, except this tree are grown sequentially. Yeah, so each tree is grown using the information from the previously grown tree. They do this way. Yeah, so they do not say, okay, you build a tree, then you put it away. They do not do that. They just keep improving this tree. Yeah, so step by step to improve it. Unlike before, we just create a lot of this kind of small detection tree, then simply combine them together. But here they just this kind of sequentially improve this detection tree. So we can take a look. How do we do? This is bootstrap algorithm for the regression tree. So certainly this is our this kind of the prediction function. We just say in the beginning we say this is 0. We consider this kind of certainly if the prediction this just means y hat this kind of the this y hat is equal to 0, then what's your residual? Residual directly for the ith observation directly is yi for all this observation in the training data. Then certainly we just create this kind of how do we grow this kind of detection tree? So for this kind of we will consider this capital B possible steps. So B is 1, 2 up to the capital B. Then we will fit the tree using this kind of the D splits. So this is capital D. If the D split, you will get the D plus 1 terminal loss. This kind of this one there to this training data. This training data is not the original training data. It consists of the X definitely is your predictor vector, but R is a residual. Yeah, you just make sure this notation you know well. This one we say this is you can say here the notation we say the Y definitely is your actual value. This is your actual value of response. Yeah, of response there. Then Y hat. This is your predicted value. Then we will use this guy. This is R just equal to the Y. Okay. We will use this residual to measure this. This is good or not. Yeah, so this is the difference of the between the actual value of the response and your predicted value. So definitely this we call the residual. Yeah, if this residual definitely R if it's 0, that's perfect. This just shows this predicted just equal to 1. So that's a reason why we will minimize the residual sum squares. RSS, you can see. It's directly is the residual sum squares. Yeah. Okay. If this one you know well, then you can say here. We use this kind of, we will work under this residual. So certainly use the residual. This is for each, for residual has measured this, the formal fitting models work well or not. So certainly you can say here, we using this one as the training data. Then we will update our this kind of the fitted algorithm by adding this kind of the in this kind of the shrunken version of the new tree. So this is the original one. Then this is your updated part. Here you also have the parameter. This lambda. This we call the learning parameter. Yeah, this is lambda we set a very small value. So every time you just improve a little bit based on your the residual, based on your your modified training data there. Okay, if this one you have done this since that, definitely your residual will be also updated. Yeah, you can say your residual will be reduced by this one, by this term, this learning term. Yeah, so will be the original Ri minus this learning term. Yeah. Okay. So you just keep doing this one. Finally, your predicted value will directly is the average value of your learning terms. This is okay? Can you follow? Yeah, you can say every time we just improved a little bit. You can say in the beginning, this kind of residual is pretty large. So we just say, okay, we just to based on this residual and the predict, we just build our data. Then we build this kind of decision tree. We want to improve it a little bit. That's just we want to make this kind of the residual become a little bit smaller. Yeah. So then certainly you just say, okay, this is our predictive. This kind of this predicted value will improve a little bit. So we will add this kind of the learned term. Certainly, if you add this learned term, then certainly your residual will be reduced by this learned term. So every time you can finally you can say each one will just improve a little bit. So you can say finally your this kind of predict we say it's this one. Yeah. So you can say this lambda times this one. So every time you just improve a little bit. Yeah, you can say this is you got it from the base tree. So here you say how many tree you have it. 1, 2 up to this capital B. So each one you improve a little bit. Yeah. Okay, so finally this boost is just the average of this learned term. Yeah. Okay. So then we can take a look at what's the idea of this kind of this kind of boosting algorithm. You know, unlike the fitting a single large decision tree to the data, certainly which is amount to fitting the data hard and potentially that will be overfitting. Actually, boosting this approach instead learns slowly. Given the current model, we fit a decision tree to the residual from the model. We then add this new decision tree into this kind of the fitted function in order to update this kind of residual. We want to make a little bit improvement on this residual, become a little bit smaller. So each of this is certain step by step. So you can say might be right now, your this kind of the grade is say, okay, the grade is 70. I just hope this kind of day by day I can improve a little bit. You say, okay, every day I can increase this kind of grade point, like the 0.1. Then finally, after 30 days or after this kind of the 60 days, you can say your improvement will be great. Even though you say, oh, one day improved only 0.1, that's too small. But finally, after this kind of 2 months, the whole improvement will be great, just like this one there. So, okay, so each of these trees can be rather small, with just a few terminal nodes. This is certainly is determined by this parameter, this kind of the number of the split. Yeah, so you say, okay, if the D is 2, then our tree only have the 3 terminal nodes. If D is 1, only 2 terminal nodes there. Okay, by fitting a small tree to the residual, we slowly improve this kind of the fitting model in area where it does not perform well. So you would say, okay, in the big, for some part, if this residual is pretty large, we hope we improve the more. Yeah, if some part we have performed well, certainly we don't improve too much. Just like certainly you guys have taken several courses. Certainly some courses you may perform very well. Some courses you you do not perform well. Certainly you want to improve the later course pretty well. Yeah. Okay, this is this one. This kind of the shrinkage parameter. This is certainly we also call it the learning parameter. This will slow the process down even further, allowing this kind of more and the different shapes of the tree to attack this residue. Yeah, this is the basic idea. This is okay. This is basic idea for this boosting. Okay. Yeah, this is certainly this we just improved a little bit. Yeah. Certainly for the boosting for the classification idea is similar like the boosting for the regression. A little bit complicated. We will not got into this detail. Actually, textbook also do not cover these details for this classification. If you are interested, you can take a look at this book, the reference book, Elements of the Statistical Learning. Yeah. In chapter 10, actually they also have a package, GBM, gradient boosted models. This is used to fit the boosted regression and classification tree for handling a variety of the regression and classification problem. Yeah. Okay, and then let's take a look at this example. We use the boosting this algorithm to the gene expression data. You can take a look at here. This for this orange, we set the D is 1. For this blue, this D is 2, the number of the split. And for this random forest, we choose this kind of the number of the possible predictor is square root of P. So you can say for the boosting, it performs much better than random forest. Yeah, you can say we only have the D is 2, so we only have the 1 split. So for your tree, what does it look like? For what this kind of small trees, just like this one. We only have 1 split, so you only have the 2, yeah, 2 this kind of the terminal nodes. So we only use this kind of so small trees, step by step, to improve this model fitting. Yeah. Okay. This is this one. Okay. We can say this is the result from the performing this kind of the boosting and the random forest on that the 15 class the gene expression data in order to predict the cancer was the normal. The test error certainly is just like before. Is displayed as a function of the trace. Yeah. This is the number of the trace. Yeah. Okay, for the 2 boosted model, this lambda, this learning factor, this is very small. It's just 0.01. For the deepest one, the trace slightly outperform the D equal to 2. Okay, and both certainly outperform the random forest. This is even though certainly the standard error a little bit high, it's around 0.02. So that's because none of this kind of difference the statistical significant. Yeah. For the test error for the single tree, it's the 24%. So you can say almost here. Yeah, 24% there. But you can say for here, for the best, the bootstrapping with the deepest 1 equal to 1. So you can say that's below the 10%, around like the 9%. So that's improved a lot. Yeah. Okay, you can see this 24%, but for the best bootstrapping algorithm, only 9%. Okay, then certainly that's another problem. Definitely is the tuning parameter for the boosting. How do we choose set the value for these boostings? One is about the number of the trees, the capital B. Another one is this kind of learning parameter or the shrinkage parameter, lambda. Third one is the number of the split. We can say for number of the trees, unlike the backing and the random forest, boosting can overfit if this capital B is too large. Even though this This overfitting tends to occur slowly. Yeah, we will use the cross validation to select this B. Another one is the shrinkage parameter lambda. This is the small positive number. This controls the rate at which the boosting length. The typical value only the 0.01 or 0.01. Under the right choice definitely depends on the problem. Very small lambda can require using a very large values of the capital B in order to achieve the good performance. But that's not a big deal because the tree you created is so small, only have the 2 terminal nodes or 3 terminal nodes. That's even though you say you create like the 1,000, 10,000, this kind of small traits. That's computationally, that's fine. Yeah. Third one is the number of the splitting the D in each tree, which controls the complexity of the boosted this kind of ensembles. Often D equal to 1 works well. In this case, tree is just the stump. Yeah, consisting of the single split, then that will result in an additive model. Yeah, you have the 2 choices. For example, less than S or greater than S, less than 5 or greater than 5. There's 2 choices there. Okay. More generally, this D is the you have only choose a single predictor. So this if you choose a larger than 1, definitely you need to consider the interaction. D is an interaction depth that controls the interaction order of the boosted model. Yeah, since D split will involve at most the D variables there. Okay, this is okay. Okay, then this is certain. Another one is the variable importance measure. For the Baggett or the random forest regression trees, we will record the total amount that the residual sum squares is decreased due to the split over a given predictor, average over the B trace. Then certainly a larger value indicates an important predictor. This is there. Similarly, for the Baggett and the random forest classification tree, we add up that kind of the total amount that the Gini index is decreased. Yeah, this is for the regression is a residual sum square. It's decreased by the split over the single predictor, still average over this kind of B trace. So you can see this is we measured for this is the hard data to list this variable importance to show which variable is important than others. So you can see that this is important this way. Yeah. Okay, and this is definitely this information is useful. Yeah. Finally, let's just summarize that. Okay, certainly here this kind of we discussed the 4 methods there. This decision tree, the bagging, random forest, and the boosting. All of them are very popular methods. They widely used in practice. Yeah. Decision trees are the simple and the interpretable models for the regression and classification. However, they are often not competitive with the other method in terms of this prediction accuracy. Bagging, random forest, and boosting are the good method for improving this kind of prediction accuracy of trees. They work by growing the many trees on the training data and then combining the predictors of the resulting this kind of ensemble of the tree. Especially for this the random forest and the boosting are among the state of the art of method for the supervised learning. Yeah, they are compatible with the support vector machines. Yeah, however, their result can be difficult to interpret. If we say decision tree, single decision tree, that's easy to interpret. But if you combine so many decision trees together, that's so hard to interpret. Yeah, this one there. Okay, and then we can quickly take a look at this kind of this kind of package and functions to do this, to implement this for method. Yeah. Okay. Certainly you can after class. I hope you guys can can just work on this kind of the R labs to read it and run the R code again. Okay, the tree library actually is used to construct the classification and the regression trees. Random forest library to use to perform backend random forest. The third package is GBM. Yeah, this is used to fit the boosted regression and classification trees. Yeah, this is a three packages. Yeah. If we do that kind of to fit in the classification and the regression tree, we will use a function is tree function. This is in this tree library to fit the regression tree or a classification tree with a response set to a factor. Yeah. The syntax of this tree function is pretty similar like the we use the LM function. The summary function lists the variables that are used as the internal nodes in the tree and the number of the terminal nodes under this kind of training errors rates. Yeah. Another function is the plot function. It's used to display the tree structure. You know the tree, this is intuitive. And the text function to display the load labels. We use the predict function to do the prediction and the function cv.tree to perform the cross validation for determine the optimal level of the tree complexity. Yeah, to determine the value of the alpha. Yeah, this is to do this kind of tree-based method. Then we do the backend of random forest. We use a random forest function in this random forest package to perform this random forest and the backend. The argument this mtry and the n trace can be used to change the number of the predictors considered for each split of the tree and the number of the trees grown respectively. By default, the random forest use this kind of the p over 3 variables when building a random forest of the regression tree. Square root of p variables when building a random forest of the classification tree. Yeah, we use the important function. Using the important function, the importance of each variable, each predictor can be viewed, and use this one. This is the variable importance plot. Yeah, this function, and this is the lot of the important measure for the regression and classification tree can be reduced, just like this one. Yeah, you can get it. Okay, and the last one is this one. It's the function for the boosting. We will use this GBM function in this GBM library to fit the boosted regression and classification tree. We will run this GBM function with the options like the distribution equal to the Gaussian. That's for the regression problem. And the option just like a distribution of the Bloody for this classification problem. In this function, this kind of the argument n.trace indicates the number of traces produced. Yeah, you can certainly the option, the interaction depth limited the depth of each tree. Yeah, you can set the value of the d. Yeah. Certain summary function produce a relative this influence plot, and also this is this output the relative importance statistic for the predictors. Yeah, certainly this for this chapter I will not run that the code there. We do not have time. But I'm pretty sure you guys have learned this R pretty well. I posted that R code in this on the canvas. You guys can study it. Yeah, to read the relevant to read the R lab and run that code. Certainly in the homework you did use it. Yeah, we have some homework relevant to use this kind of boosting and deletion trace. You can, yeah, you can use this function to do it. Yeah. Any question? Okay, if low quality, certainly we study, certainly I told you for the second half part, certainly we will introduce more and more this kind of the popular algorithms. Certainly we will cover more and more material there. Certainly next class we will move to introduce the chapter 9 about the support vector machines. Certainly, for the last, I guess the um, last class we will cover the chapter 10. Then this is about the clustering, about the unsupervised learning. So for this class, we'll cover all these 10 chapters for this textbook. I hope after class you guys can read the relevant chapter to do some practice. Yeah, to do some practice, especially with this R level there. Actually, this book is a pretty popular book. You can easily use the Google to do some search. You say there are so many this kind of the web pages on this book. It seems this book will, I guess, they will have the second edition. Second edition published in the, I guess, in this summer. Yeah, so you can get it. Usually, they will provide they will be freely available for the readers, so you can quickly get it. Yeah. Any other question? Yeah. Okay. If no question, let's just stop here. I just hope after class, you guys can spend some time to really work on it. Certainly I know for this online teaching is pretty challenging to all of your guys. But if you really want to learn something, especially for this kind of the machine learning, data science, or whatever, you really need to spend the time to work on it. A lot say, oh, this is a pretty popular subject. Yeah, in the future I can use this one to find some job or to work on to have a pretty bright the future career. But if you do not spend the time work on it, no matter what kind of the field or topic, that's not really help you a lot. And I'm pretty sure only when you know this kind of field really well, you can get a lot of this kind of job opportunities. Yeah, I remember right now I also have the 2 PhD students who work on this kind of machine learning. Certainly they got a number of this kind of internship opportunity, this interview opportunities for that one. I know there's more popular there, but another one still there. You did really know this kind of subject well. Not say, okay, I have taken this class. But if you know nothing very quickly during the interview, they know, oh, you know well or you do not know well. It's okay. I really hope you guys can spend some time to work on it. Yeah. Okay. If no question, let's just stop here. Okay. Thank you.